I'm Carl Spandler, and I'm talking on behalf of my co-authors as well, Bob Henderson, Elliot Foley, Eric Roberts, and Tony Kemp at the various partner universities here, James Cook University and University of Western Australia, and I'm from the University of Adelaide. I'm going to talk today about some magmatic rocks that are found that we've been working on in southeastern Queensland and what implications they may have had for the Cretaceous tectonic setting of Eastern Australia. This very much follows on from Elliot Foley's presentation in this session, and this slide is very similar to his. Just to set the scene here, to run through this quickly, what we know about Eastern Australia is that it developed in the Phanerozoic largely due to accretionary orogenic activity known as the Tasmanides. A series of origins that extended down to about 220 million years ago in the New England origin, and then the period after that is a little bit mysterious, but we do know that there was the Whitsunday volcanic province forming at around 130 to 90 million years ago, based on largely on the volcanic rocks that are exposed in the Whitsunday Islands. These are believed to be a silicic large igneous province, possibly related to a mantle plume, and not obviously linked to convergent margin tectonic regime. That's the current understanding of Whitsundays. Following that, we know that the eastern margin of Australia was dominated by extension. We've had stretching of the crusts, submersion of a lot of continental crust, for example, in the east, in the Lord Howe Rise, and migration of the plate margin out into the Pacific to lead to the current tectonic regime. What we don't know very well is what happened across most of the Mesozoic in Eastern Australia. So the Jurassic and into the Cretaceous, what was the tectonic setting along this eastern margin? We know that there was large amounts of sediment deposited into the Great Artesian Basin, and that's the focus of Elliot's talk. Today, I'm going to talk about a suite of rocks that we've been looking at in southeastern Queensland, inland of the Sunshine Coast and Fraser Island, in this blow up here, and I'll also be talking a little bit about the Whitsundays as well. So the rocks, specifically we're looking at these very scattered plutonic and volcanic units found at Noosa, Coolum and inland, and a volcanic sequence known as the Graham's Creek Formation, shown here in green, which is a fairly significant package of volcanic and volcaniclastic rocks that probably make up something like 250,000 cubic kilometres of material, so not insignificant. In a very simple stratigraphic sense, this is what it looks like. So these intrusions have intruded into the Nambour Basin, which is Jurassic in age, and partly into the Graham's Creek Formation as well, which is earliest Cretaceous in age at the base of the Maryborough Formation. And for various reasons, we see this as a separate igneous package of rocks that we've named the Morton Igneous Association. Very quickly on petrography, the intrusive rocks are quite fresh. We see everything from gabbros to diorites through to granites and even quartzianites in a few cases. The more mafic end, well, all of the intrusive rocks really are fairly distinct in that they have an abundance of igneous amphibole, as you can see in these images here. There's a hornblende gabbro with these fresh igneous hornblends, and there's a hornblende andesite again with these large porphyritic hornblende crystals. The Graham's Creek Formation is a little bit more altered, but we still see well-preserved volcanic textures, igneous textures, lots of plagioclase phenocrysts in cases variably altered, in some cases some remnants of fresh pyroxenes as well. In terms of major element geochemistry, here's a series of Harker plots just to show you the variation across these suites. We've got the Morton Igneous Association rocks. The intrusive rocks are shown in red, and volcanic rocks of the Graham's Creek Formation in green, and they're compared to some data from the Whitsunday Igneous Province in blue. We see the large range all the way from mafic to felsic compositions, and we see trends that are fairly consistent with crystal fractionation or fractional crystallization across this suite. The two sets of rocks are fairly similar, but a notable difference is in the titanium content. We see in the bottom left that the Whitsunday rocks are distinctively more enriched in titanium than the Morton igneous rocks. In terms of trace element geochemistry, we can see some very quite fundamental differences. So these are spider diagrams, if you like, of incompatible elements normalized to N-Morp on the vertical axis. So a mid-ocean ridge basalt would plot at 1 here. So various samples of diorites and gabbros mafic rocks from the Morton Igneous Association are shown here. They have a very consistent pattern with this distinct enrichment in incompatible elements and depletion in niobium, tantalum, and titanium, which is a classic subduction-related signature. In fact, a very classic continental arc geochemical signature. Graham's Creek Formation, the second plot here, panel here, it shows a little bit more scatter because they're altered and some of these elements have been moved by alteration. But we again see these distinct niobium, tantalum, titanium anomalies, very similar to the intrusive rocks. And so the relationships between these magmas can be made here. There is a relationship, and again, classic continental arc geochemical signature. In terms of trace elements, in the Whitsunday rocks, we've got some mafic rocks that we collected from South Mole Island shown here. Again, enrichment in incompatible elements, but we're not seeing in this case the very distinct deep niobium, tantalum, titanium anomalies that we saw in the Morton igneous rocks. There is a slight anomaly in niobium, tantalum. There is some subduction related influence, but nowhere near to the degree that we see in the Morton rocks. And that's really expressed well in the second plot, which is thorium ytterbium versus niobium ytterbium. This is used to differentiate mafic magmas by their tectonic setting. You can see the Morb array plotted through the middle there. Continental arcs in sort of tan brown up the top, and you can see the Morton igneous rocks plotting very much in the continental arc field. The Whitsunday rocks are plotting from close to the Morb array for the most mafic rocks, and then as you increase silica up towards the rhyolites, they're extending upwards in their thorium ytterbium ratio. And these fit quite nicely into an enriched back arc field or a continental back arc type setting. And that's what we're interpreting here, is that the Whitsunday rocks are consistent with a continental back arc setting. In terms of the age of these rocks, the Morton igneous rocks, there's probably more than a dozen of these rocks that we've got good ages out of, uranium lead zircon ages out of. Here's a couple of examples here of one sample of the Graham's Creek Formation and one of the intrusive rocks. And we see very consistently we're getting ages coming out. These two here are around 140 million years old. There are a few that go slightly older to 145. And there is some detrital signatures in here as well. But the igneous age is consistently between 140 and 145 million years old. Hafnium isotopes on these zircons give numbers, initial hafnium isotope signatures of +7 to +12, so very primitive values consistent with derivation of these magmas from a mantle source, irrespective of whether they're mafic or felsic. So fractional crystallization is an important process in the evolution of these rocks. So what we interpret here is that in Eastern Australia there was an earliest Cretaceous around 140 million year continental arc setting in Eastern Australia, with Sundays, which is distinctively younger, 5 to 10 million years younger at least than the Morton rocks. We're interpreting that to be a continental back arc. So the margin evolved from a continental arc to a continental back arc in the early Cretaceous. So to sum that up, really a modern analogue for what we think is going on can be seen in the Okinawa Trough, south of Japan, where we have continental crust, continental arc. In northern Pacific here, subduction rolling backwards to the south east, and we've got extension in that submerged continental crust between Taiwan and Japan, and we have a continental back arc forming in that environment. And so this is the kind of tectonic setting we were envisioning for Eastern Australia in the Cretaceous, with the back arc forming as the subduction zone, as the slab starts to roll back and the trench migrates eastwards into the Pacific. All right, to sum up,